Hello guys, welcome back once again. So we'll look into another problem which contains a PMOS, and they have asked about to sketch Ix as a Ix and transconductance as a function of Vx. So the given MOSFET is a PMOS, and they have given the threshold voltage, and there is no body effect and all. Body effect and also channel in modulation is also not present, and Vx is varied from 0 to 3 volts. Now before going to solve this problem, we have to remember one thing is in PMOS always source is at highest potential than drain. Source is at highest potential while drain is at lowest potential. In the NMOS it's the other way around. So now we shall vary Vx in increments, so and we'll be able to plot, and we shall obtain Ix and Gm in terms of Vx. Now we shall start Vx from 0 volts. So when Vx is 0 volts, I will label it as node A and node B. So when Vx is 0 volts, as mentioned in PMOS, whenever the terminal having highest voltage will be called as source terminal, whereas the terminal with lowest voltage is called as drain terminal. So we can clearly see when this is at Vx is 0 volts, node A would be drain and node B would be source. Node A is drain and node B is source. So first thing, we want Ix and Gm in terms of Vx. First, in order to find out Ix, we have to find whether the MOSFET is operating in saturation or not. Based on that, we can use Ix correspondingly. So we shall find whether the MOSFET in triode or saturation. So we shall evaluate VGS. So VGS is Vg minus Vs. Vg is at 1 volt and source is at 1.9 volts, so it would be minus 0.9 volts. We are checking whether first MOSFET is on or not. So VGS is minus 0.9 volts and threshold voltage is minus 0.8 volts. Clearly this inequality holds true, which indicates the MOSFET is on. So the next condition is whether it is in saturation or not. For PMOS, in order to be in saturation, the condition is VDS should be less than VGS minus VT. So VDS is VD minus Vs and VGS is VG minus Vs. We can cancel this Vs and Vs. So VD, drain is at 0 volts and gate is at 1 volt minus, and threshold voltage of PMOS is minus 0.8 volts. So 0 less than 1.8 volts. So this holds true. This holds true. So the MOSFET is in saturation. So once we got to know that MOSFET is in saturation, we shall use the equation ISD equal to, so in PMOS always the current flows from source to drain. So since B terminal is source, so the current flows from node B to node A, and clearly ISD is in direction opposite. Ix is somewhat opposite to ISD. So ISD is nothing minus is equal to minus Ix half mu n Cox W over L times of VGS minus VT whole square, and we shall normalize Ix by mu n Cox W by L is equal to minus half into VGS minus VT. We just obtained VGS minus VT as minus 0. VG is at plus 1 volt, whereas source is at 1.8 volts, and threshold which is minus 0.8 volts square. So this would come around minus 0.005. so Ix by normalized value of Ix is minus 0.0005. Similarly, trans conductance Gm is given by, in saturation is given by un Cox W by L times of VGS minus VT. We shall normalize this trans conductance by mu n Cox W by L, so VGS minus VT. So when we substitute the values and we obtain is minus 0.1. See, the reason why we obtain trans conductance as negative, because the current obtained here is also negative, so only we are getting trans conductance as negative. So this is the Ix and normalized value of Ix and Gm in saturation. So this would be a constant until MOSFET is in saturation. So now we have to find up to what value of Vx, so that this will be the same up to that value. So we have to find what is that Vx value, up to what is that range, so that normalized value of Ix and Gm would be the same as these two. So that is nothing but we have to find what is the value of Vx, for which it will go out of saturation. It is in the edge of the saturation. So saturation condition is given by, so I will be cancelling Vs and Vs here. So Vd will less than or equal to minus Vg minus Vt. So Vd, so drain voltage, Vx is at drain voltage and Vg is at 1 volt, and threshold voltage of PMOS is minus 0.8. So Vx would be less than or equal to 1.8 volts. So Vx less than 1.8 volts, up to this range the PMOS would be in saturation, and it will be having normalized value of Ix and Gm as shown here, these two. So now consider another case where this node voltage B is fixed at 1.9 volts. So what happens exactly when Vx is also 1.9 volts? Consider that case. So considering the case, Vx is equal to 1.9 volts, then this potential and this potential are equal, then definitely there won't be a current flow, because drain and source are at the same potential. So drain Vd is V equal to Vs, so which implies Ix is almost approximately equal to 0 and trans conductance is also approximately equal to 0. Now we shall consider a case which is where Vx is greater than 1.9 volts and we shall take a number which is the upper range of the Vx, which is 3 volts. So we know here the condition when Vx is less maximum 1.8 volts, it was in saturation. Once Vx crosses this 1.8 volts, it will go out of the saturation and it will reach the triode region. So now the current and transconduct equations, we have to use that as of current equations in the triode region. So now node A would be source and node B would be drain. Now these two got interchanged. Now node A would be source, node B would be drain. As the reason is simple, PMOS in PMOS source is at highest potential, drain is at lowest potential. So now we have to obtain ultimately Ix and Gm in terms of Vx. So we shall use the equation which is Ix. So this is at source potential. So source to drain current flows something like this, and also Ix current is also flowing in the same direction. So Ix is nothing but source to drain current. So here Ix and both are in the same direction, there won't be any negative sign. So since PMOS is in triode region. We will be using the equation of that triode region, VGS minus VT, VDS minus VDS square divided by 2 bracket. So once we evaluate this, we shall normalize it with mu n Cox W over L. So we will be obtaining value as 0.715 after substituting all the values. Similarly, for transconductance, which is normalized value of transconductance mu n Cox W over L VSD. So this would be around Vs minus Vd. So Vs, which is at highest potential, that is 3 volts, minus Vd, which is at 1.9 volts Vd. This is at node B is at drain terminal, which is Vd. This is 1.9 volts. So 1.9 volts. So 3 minus 1.9 volts would be 1.1. Since current is also positive, the transconductance would be also positive too. So the main reason being, whatever the MOSFET current, that is source to drain current, is in direction with the same of that of Ix. That's the reason the current, both the current and the transconductance are positive. Now we shall plot Ix and Gm as a function of Vx. So plot of Ix as a function of Vx. So in x-axis Vx is varied, in y-axis normalized value of Ix is varied. So when Vx is 0 volts, we had obtained Ix, normalized value of Ix as somewhere minus 0.005, and when Vx was 1.9 volts, we obtained Ix as 0, approximately equal to 0, and when Vx was 3 volts, when Vx is 0 volt, when Vx was 1.9 volts, when Vx was 0 volts. So when Vx was 3 volts, almost the normalized value of current was somewhere 0.715. Now we shall be connecting these points. Ix, normalized value of Ix and Vx are related by quadratically. So the waveform will something look like this. There is a square relation between Ix and Vx. When Vx is increased, Ix is also getting increased. Ix and Vx are not linearly related, they are related quadratically. So the waveform will look something like this roughly. Next we shall plot transconductance as a function of Vx. In y-axis I will be plotting normalized value of Gm. In x-axis I will be plotting Vx. So when the Vx was around 0 volts, we had obtained normalized value of transconductance as minus 0.1. When Vx was 1.9 volts, we obtained transconductance, normalized value of transconductance almost approximately equal to 0 when it was 1.9. When Vx was 3 volts, we obtained transconductance somewhat 1.1, normalized value of transconductance as 1.1. Now we shall connect these 3 points. So we have to remember one thing is Gm is related to Vx by a linear function, and when Vx is increasing, normalized value of transconductance also increases linearly. When Vx is increasing linearly, obviously normalized value of transconductance also increases linearly. So the plot will look something like this linearly. So I am indicating the linear by a straight line. So this is what they had asked in the question: plot Gm and Ix and Gm as a function of Vx. Thank you.